Hey everyone, Isaac here. Today we're going to have some fun with the PennyLane team, which is host to some of the highest caliber keyboard slinging programmers in the game. But how much do these QWERTY Jedis rely on sight to make PennyLane the best quantum programming software package in the galaxy? We have 5 eager and competitive PennyLane developers and researchers who have volunteered to put their keyboard wizardry to the test. Here are the rules. Each person will be given the same task where they can only trust their fingers. The task involves code that's relatively simple. None of the competitors have had a chance to see this code or know of it at all. They are going in completely blind. They must create a data set that's of length 2 to the 10. This data must be encoded on a 10-qubit device using PennyLane Lightning, which is PennyLane's super fast quantum simulator device. The circuit must have a specific multi-controlled X gate, Hadamards in every qubit. After they create the circuit, they have to define a simple cost function and optimize it just once, printing out the result. Each person will start with 100 points. 2 points are deducted for every syntax error, and 1 point will be deducted for every non-code breaking error. First up is Josh Isaac.
Yeah, so my name is Josh. I'm leading product here at Xanadu. I've been here for a while now, like almost 6 years, I think. So I helped sort of, at the very beginning, building up PennyLane to what it is now across the documentation, the library. And I would say my favorite feature of PennyLane is probably the parameter broadcasting we have, the fact that you can pass multi-dimensional parameters when you're working with quantum circuits.
Next up is Matthew Silverman.
Hey, I'm Matt. I'm a quantum software developer here at Xanadu on the PennyLane core team. My background is more like classical software infrastructure. One thing that's really exciting for me is the all-new device API that we've been working on. So that's coming soon.
After Matt, we have Guillermo Alonso.
Well, hi everyone. I'm Guillermo. I work here in Xanadu in 2 different teams, in the community and in the algorithm team. And I'm doing some research, for example, in quantum phase estimation right now and some methods. And a feature that I've been working in that I really like was the barrier. That is one of those operators that seems useless, but actually they are really important.
Following Guillermo, we have Christina Lee.
I'm Christina. I've been with Xanadu for 2.5 years, and I'm the tech lead for the core squad developing PennyLane.
And for the cherry on top, we have Utkarsh Azadi.
Hello, I'm Utkarsh. I work in the algorithms team here as a quantum scientist, and I've been majorly working on quantum chemistry sides of things. But one of my favorite features that I've implemented that's very recently is on the quantum datasets.
Will their muscle memory deceive them? Let's find out. So, you're going to need to import PennyLane as QML probably.
Oh no, I think I sent a typo already.
Oh shoot, I already lost track of where I am.
As QML or however you want
I like it.
to. Okay, and then you're going to need PennyLane's wrapped version of NumPy.
Okay.
All right, so you've imported NumPy, awesome. Next thing you want to do is create this this data. So call it whatever you want. X data params, cool. NumPy random uniform parentheses, then 2 to the 10. Define that data. So X data, call it whatever you want. Cool. And NumPy random uniform. Okay, and then the lower bound on the interval is 0. The upper bound is 1, and then the size is 2 to the power of 10. You want to define a device?
Yeah.
Yeah, that runs on PennyLane Lightning. Cool, and it's got to have 10 qubits. Now you can get creating your circuit. So you want to define a device that uses PennyLane Lightning.
Yes, that's a good one. And then that qubit. Okay, that sounds good.
And then create the Q node?
Yeah, this circuit's going to be a Q node. Yeah, you got it. No fancy differentiation methods or anything. Okay, cool. So your circuit needs to take in the data that you created.
Yep.
And then also some variables that we'll call thetas or angles or whatever you want to call it.
I'll call them X.
X, okay, cool. So these are like your variational parameters.
Yep.
Cool. So you're going to want to do amplitude embedding.
Please. embedding.
Cool. You are going to want to give it your parameters, params, you called them. Okay, and it's going to go on all the wires, so you need to give it the wires keyword argument.
Interesting. Y is equal to h10.
So the next thing you need to do is normalize equals true.
So am I on X or where am I?
If you start typing normalize equals true right now, you're fine.
Oh,
Yeah, so normalize equals true. Okay, so next you're going to want to embed the data. So you're going to want to do qml.amplitude embedding. Okay, cool. You're going to want to give it the data, x. And yeah, wires is range 10, like it put it on all the wires. Okay, cool. And then you're going to make sure the data is normalized. So comma space, normalize equals true. Sweet, because the next operation you're going to do is a Hadamard gate on every qubit.
Oh, I prefer.
For loop.
Yeah.
Yeah, okay, so for I in range
Let's say 10.
10, okay, qml.hadamard.
Okay. Let's go.
Perfect. Now, put a Hadamard gate on every qubit.
this always reminds me to, like, we should allow single qubits to have multiple wires.
Oh yeah, that's
that
good.
would be
that'd be a good PennyLane feature. Okay.
Yeah.
So for I in range 10, yeah.
Oh no, QML.
Hadamard. Alright, cool. All right. The next gate you want to do is a multi-controlled X gate.
You're just picking this because it's a really long name, right? You're trying to get me.
And the arguments suck. Okay. Now the control wires are going to be.
I think I just clicked the trackpad.
You did. Okay,
shoot.
cool. I'll go back. And the list of wires is going to be 0, 1, 2, 3, 8.
Nine.
I think that's 8.
Okay, cool. The next argument is going to be the target wires. So the target wire is going to be 7.
Target wire is going to be... let's go with... Oh, shoot. I'm really not good with the numbers. Ooh. Let's say that.
Okay. Right on. Okay, and then the next thing you need to do is like your control values. So that needs to be a string. And the control values are going to be 0, 1, 000.
0, 1, 0, 0, 0.
Yep, cool. So you're going to create 10 RX gates, and the angle is going to be the corresponding entry of X that you made.
Okay.
Whatever.
For I in range 10, qml.rx x bracket I bracket parentheses. No. Wires equals okay.
Yeah.
Yep.
And then you're going to return the expectation value of the poly z operator on every qubit.
Oof.
Yeah, qml.ext val of for I in range 10. Cool.
I will say it's like here. Okay.
Okay. So qml.exp val
As well.
poly z.
Okay.
I, right? For I in range 10. Awesome. Okay, that's your circuit.
Perfect.
Cool. All right, so that's your circuit. Now you're going to do a cost function. Cost. And it's going to take your params as an argument, and that's it. Okay? You're good? All right, so it's going to be super simple. You're just going to return the absolute value of the sum of all of your circuit outputs.
Absolute value of.
The sum of your circuit output.
Oh,
So
okay.
yeah,
okay.
just return.
Okay, so I have vals equals circ. So
So your circuit took in
X.
X. Yeah, so you're going to type return.
Okay. Return np dot.
Abs
No.
of sum or np.sum
So np dot sum.
of
That's
vals. Yeah, there you go.
Def cost.
Cool. And it's not going to need the data you made.
So
put
just
in it.
X?
Just X. Cool.
Okay, so return np.abs
Abs. Yeah.
of np.sum
Yep.
of circuit
Circuit
of x.
of data index.
Oh yes, data x. Close
Cool.
bracket, close bracket, close bracket.
Cool. Next thing you need to do is create these angles. So they're going to be randomly randomly sampled between 0 and 2 pi uniformly. So call them angle
equals
numpy
dot
random
dot
uniform
uniform
0 and 2
0
pi.
2 times pi.
Cool.
Oh.
I think you need to actually give it size. Yeah.
Size equals 10. Yeah.
Now you need to define your angles that you're going to optimize. So call them angles. That's what you call them in your function. And it's going to be sampled uniformly random in between 0 and 2 pi. And then there's 10 of them. Yep. Only 2 more things. You need to create an optimizer. So Atom seems to be the easiest ones to type in. So qml.atom optimizer seems good. And do a step size of 0.5. Okay, you need to define an optimizer. You can do atom or gradient descent, whatever your choice, doesn't matter. Atom optimizer is what it's called in the docs. Optimizer. And give me a step size of 0.5.
0.5.
Yep.
That's brave.
You're just going to print op.step and cost.
Oh, I think I just hit P by accident. I'll just assume I did.
Opt.step and cost. You're going to give it the cost function you made and your angles that you made. Angle. And so give it your cost function. And
I think I just made a typo. Oh well.
Okay, cool. Okay, so you're done. All right, so you're done. How do you feel you did?
I feel I did terribly.
You did terribly.
Yeah.
Okay, so you're done. Don't take your blindfold off yet. How do you think you did? On a scale of like 0 to 10, 10 being perfect, like how do you think you did?
I'm gonna say a 6.
A 6, okay,
I mean,
cool.
the problem are going to be the columns and the numbers, probably.
Okay, cool. You need blindfold on. How do you think you did? On a scale of 0 to 10. 10
Badly.
being
Badly.
badly? So on a scale of like 0 to 10, 10 being like perfect, how do you think you did?
4.
Honestly, not so great.
Not so great?
Not so great. I think I got a lot of the numbers wrong.
Yep, that's bad.
Yeah.
It's perfect. Oh my god, what is this print doing here?
Oh my god.
You actually did pretty good, mate.
Ooh.
You did pretty good. You could send this. It's pretty impressive. It's not bad. Hopefully everybody had a good time. I have to say, I didn't have to like re-normalize any scoring or anything like that. Sometimes the scoring was difficult. So just to recap, the scoring rules I was going by were you start with 100 points and then every syntax error you make, it's 2 points off of your total and then 1 point for every non-code threatening issue. It was a little hard sometimes to like assess that, but I think on the whole, I think how everything shook down, there's a clear winner. Don't think of the number so much as just where you're placed. In first place, we of course have Matt. Matt, I don't know how you did it. Like, you got 82. Matt, excellent job. Your keyboard wizardry is put on full display here. Excellent work. Next PR you make to PennyLane should be totally blind. So, great job, everyone. Matt, do you have anything you'd like to say? Any people you'd like to thank?
Yeah, I mean, obviously, I'd like to thank the Academy. I'd like to thank everybody who put the time in to make this production. I think I maybe 5 to 10 times felt for those little like bumps on the F and J letters to align my hands, and I thought I was going crazy. But I see now that was my saving grace.
Da, 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 da. All right.
Good.
Yeah, so you don't need to put it on super tight or anything, just whatever's comfortable. Okay, cool. You can't see anything? Yeah, go ahead.
Roll.
Yeah, we're rolling.
Cool. Awesome.
Josh took a long time to decide for us because he's like been here for like 6 years. He's like done everything up until now. Go ahead. Yeah.
I thought you were going to do something.
Oh, I have notification addiction.